Given question, draw shear force diagram and bending moment diagram of simply supported beam carrying uniformly distributed load and point load.
This is the question of simply supported beam carrying point load and uniformly distributed load. To draw the shear force diagram and bending moment diagram, first step is to draw the free body diagram. If we observe uniformly distributed load, then it is given 2 kN per meter over the span of 2 meter. So total load is equal to 2 multiplied by 2, that is equal to 4 kN, and the point of application of this force, that is the center of gravity point, is the center point. So we will plot this in the free body diagram. So here is the span of 2 meter and we will select the middle point. And this middle point for the span of 2 meter is the center of gravity point for the uniformly distributed load. So I will show this, and it is equal to 4 kilonewton. Now this is the question of simply supported beam. So the reactions at point A and reaction at point B are in vertically upward direction. So we will show here with RA and this is with RB. Now we have to find out the values of RA and RB. So we will consider this body is in equilibrium. So we can write this summation of all vertical forces is equal to 0, and we can take the summation of the moment of all the forces about any point. We can select either A or B. About the point A is equal to 0. So we will select here the point A. So first, when we take the summation of all vertical forces, if we observe 1 kilonewton, 4 kilonewton and 4 kilonewton in downward direction, and RA and RB in upward direction. So we can write here RA plus RB is equal to 1 plus 4 plus 4 is equal to 9 kilonewton. So this is the equation number 1. We will take summation of moments of all the forces about point A is equal to 0. Now if I move the compass in the direction of this 1 kilonewton force about point A, then it is in clockwise direction. So for clockwise direction, we will select here with positive sign, and for anti-clockwise direction, we will select negative sign. So how to take the moment, that is force multiplied by the distance in between A and this point, that is 1 multiplied by 1. Then next is 4 kilonewton. So again, if I move the compass about point about in the direction of 4 kilonewton about point A, then it is also in clockwise direction. So we can take here plus 4 multiplied by this total distance. So this distance, half distance is 1. 1 plus 1 plus 1, that is 3. Next is 4 kilonewton. So this is also in clockwise direction. So plus 4 multiplied by this distance is 5. Then we will move to the last RB. So if I move the compass about point A in the direction of RB, then it is in anti-clockwise direction. So we will take minus RB multiplied by the distance, total distance is 6, is equal to 0. Now when we solve this, then we will get RB is equal to 5.5 kilonewton. Now if we put this value of RB in equation number 1, then we will get RA is equal to 3.5 kilonewton. So we will mention here RA is equal to 3.5 kilonewton and RB is equal to 5.5 kilonewton. Second step is the calculation of shear force and bending moment. We will first calculate shear force. So it is the summation of all the forces either on the right hand side or on the left hand side of the section. We have to calculate the shear force with these sign conventions, and we have to mention these sign conventions in the answer sheet. we will take the summation of all the forces which are on the right hand side of the section line. Now if we observe, when these forces on right hand side are in upward direction, then we have to take the negative sign, and when the forces are in downward direction, then we have to take the positive sign. Now we will consider the section FB. Now for this section I will show here the section line. Now we are going to take the summation of forces which are on the right hand side. So how to write this? So shear force, that is SF, in the section F to B. So on right hand side there is only one force which is in upward direction, and it is 5.5 kilonewton. So we will consider this with negative sign, that is minus 5.5 kilonewton. Now we will move to the next section, that is section EF. So again I will calculate SF, that is shear force, in section EF. So we have to show this section line. So here is the second section line. Now we have to take the summation of forces which are on right hand side. So here this force is in upward direction and 4 kilonewton is in downward direction. So for upward direction I will take minus 5.5 plus, because 4 is in the downward direction, plus 4. So if we calculate this, then we will get minus 1.5 kilonewton. Now we will move to the next. Now if we observe, next section is this DE, but in this DE there is uniformly distributed load, and this uniformly distributed load, shear force, will vary linearly. So we will calculate the shear force in the section C to D. So I will write here SF in section C to D. So we have to show this section line in between C to D. Now how to calculate this? So we have to take the summation of forces on right hand side. So RB, that is with minus sign because it is in upward direction. So minus 5.5 plus 4 plus 4. So we have to take 8 minus 5.5, that is 2.5 kilonewton. So if we observe here, this 8 minus 5.5, that is plus 2.5, so we will give here the positive sign. So this sign is important. Now we will move to the next section, that is the section in between AC, SF, AC. So I will show here this section, then we will calculate this. So again we have to take this minus 5.5 plus 4 plus 4 plus 1. So it is plus 3.5 kilonewton. Now we have to plot all this data. Now if we observe, the shear force due to point load will remain constant. So how to show this? So first we will plot the data. We have to first take one baseline, and we have to take, here is the point A and this is the point B. Now the shear force in the section FB. So this section is due to this point load. We have calculated the SF value due to the point load. So this section is having with negative sign minus 5.5. So whenever there is negative sign, we have to plot the value in the downward direction. So we will plot here minus 5.5, that is, I will take here minus 5.5. Now this section FB, this value will remain constant because this is the shear force value due to the point load. Now next is EF. So here is EF. Now during this EF, value is minus 1.5. So this will also remain constant. So we have to take here minus 1.5. So I will select here the value with minus 1.5. So this, during this section EF, it will also remain constant. So I will plot here the letters C, D, E, F, C, D, E, F. Now we will connect this. connect this. So next point, CD. So for CD, it is also due to the point load, it is plus 2.5. So for this CD, span CD, we will plot the value plus 2.5. So I will plus 2.5. So we have to plot this in the upward direction because of the positive sign. Then next AC. So during AC, it is plus 3.5. So it will also remain constant. So we have to show here plus 3.5. Now we will connect this. Now these are the constant values due to point load. But what about the span D to E? Now this D to E span is uniformly distributed load, and we know that shear force varies linearly due to uniformly distributed load. That means we have to join these 2 points, that is at point E shear force is minus 1.5 and at point D shear force is plus 2.5, and in between DE it will vary linearly. That means we have to show here straight inclined line. So this is due to the uniformly distributed load, and here is the point of intersection. So suppose I will consider this point of intersection will be P. Now main question is we have to find out the distance of this P from this point D or from this point E. So how to find out? So for that we will make one construction. I will connect here this triangle. Now we will consider this point will be R and this point will be S. Now here are two triangles RDP and second triangle PES. So we will find out this distance from these two triangles. So how to find out? So I will write here from triangle RDP and from triangle SEP. Now we will take the ratio from base to the height. So from this triangle base to the height line, that is DP. This is the base. So I will write here DP divided by this height is RD. RD is equal to. Now in the same way we will take here is the base. So base is PE. And height is ES. Now we will put the values. So if we observe, here is DP as well as PE, both are unknown. So how to write this DP in terms of PE? Because the total distance from D to E is equal to 2 meter. So this DP is equal to 2 minus PE. So we will write here 2 minus PE divided by RD. So for this RD we will consider magnitude only, that is 2.5 is equal to PE divided by ES. So for this ES, so this baseline is having 0 value. So it's a value with magnitude 1.5. So we will consider magnitude only. So when we solve this or when we simplify this, then we will get PE is equal to 0.75 meter. So we will mention this distance 0.75 meter. Now we will calculate bending moment with this sign convention. So we have to mention these sign conventions in the answer sheet. Now when to calculate the bending moment, we can take the summation of moment of all the forces either on the right hand side or on the left hand side of that selected point. If we observe here, the point of intersection with this horizontal line and vertical line is the selected point. And for this question, we will take the summation of moment of forces which are on the right hand side. So when the moment is in anti-clockwise direction, we will take the positive sign, and when moment is in clockwise direction, we will take the negative sign. So how to calculate bending moment at point B? So if we observe, there is no any force on the right hand side. So bending moment at point B is equal to 0. Next is bending moment at point F. So on the right hand side here is the point load, and if I move the compass about point F in the direction of RB, then it is in anti-clockwise direction. So we have to take positive sign. So plus 5.5 multiplied by this 1. Then next, bending moment at point E. So if we observe, there are 2 point loads. So this load is in anti-clockwise direction. So we will take plus 5.5 multiplied by distance in between this E and this RB. So it is equal to 2. Then if I move the compass about point E in the direction of 4, then it is in clockwise direction. So minus 4 multiplied by distance in between EF is equal to 1. Now next is bending moment at point P. So this is the point of maximum bending moment, and it is necessary to calculate bending moment at the point P, because at this point shear force is 0. So how to calculate this? So if we observe, this point P is in between this section D to E, where this section D to E is with uniformly distributed load. Now we will consider here the point P, which is having distance 0.75 meter. So we will mention this distance from this point E. So we will calculate this. So if I move the compass about point P in the direction of RB, then anti-clockwise direction. So we will take plus 5.5 multiplied by distance in between PB. So it is 2.75. Then if I move the compass in the direction of 4 kilonewton, then here is the clockwise direction. So minus 4 multiplied by distance in between PF. So it is 1 plus 0.75, that is 1.75 meter. Now again in between P and E. So this P and E, if we observe this 0.75 meter span, then it is having uniformly distributed load, and this uniformly distributed load is with 2 kilonewton for 1 meter. So what is this load at this 0.75 meter? So for over the span of 1 meter, load is 2 kilonewton. So for the span of 0.75 meter, how much load is there? So this value of x is important. So how to calculate this x by cross multiplication? So this load is equal to, we can take here 1 multiplied by x is equal to 2 into 0.75. So this load is equal to 2 multiplied by 0.75 kilonewton. So this is the load, and where is the point of application of this load? That is the center point, and this center point is in between this 0.75 meter span. So how to calculate this? So we have to calculate this with 0.75 by 2. So this point of application is at 0.75 by 2. So how to select this moment? So we know that moment is equal to this load, this kilonewton, multiplied by the distance, which is in meter. So how to take the moment? This load multiplied by 0.75 by 2. Now this load which acts at the center point of PE is in downward direction. So if I move the compass about point P, then it is in clockwise direction. So we have to take the negative sign. So minus, we have to take this load 2 into 0.75 multiplied by 0.75 by 2. So this is the calculation we have to mention in the question. Now when we calculate this, then we will get the maximum bending moment at this point P. Now we will move to the next bending moment at point D. So if we observe, again we will consider here from this point D, if I move the compass in the direction of RB, then we will get plus 5.5 multiplied by distance in between D and B is 4. Then here minus 4 multiplied by distance in between D and F is 3. Then next is this 4 kilonewton. So this is the uniformly distributed load, and this point of application is the center point of DE. That is, from this distance D to this point of application is the center point, that is 2 divided by 2, 1. So how to write this? So it is also in clockwise direction. So minus 4 multiplied by 1. So this is the bending moment at point E. Now we will calculate bending moment at point C. So again we will calculate this plus 5.5 multiplied by this distance. 1 plus 1 plus 1 plus 2, that is multiplied by 5. Then minus 4 multiplied by, so this distance is 4. Then minus 4 multiplied by, this distance is 3. So we have to calculate this. Then bending moment at point A. So again we have to calculate plus 5.5 multiplied by this total distance. 2 plus 2, that is 6. Then minus 4 multiplied by this 5. Minus 4 multiplied by 2, here is 1. So this remaining distance is 1. We have to take. So this 1 plus 1 plus 1, that is 3. Multiplied by this 1 kilonewton, that is multiplied by, here is minus sign, minus 1 multiplied by 1. So we have to calculate all this. Bending moment at point C is 5.5 multiplied by 5, because the distance is equal to 5. Then for this minus 4 multiplied by this distance is 4, and here minus 4 multiplied by this distance from C. So this is the center point. So this distance is 1 plus 1, that is equal to 2. So when we calculate the values, we will get the answer. Now bending moment at point B. So we have to first show the baseline, and on baseline we will show the point 0. Then bending moment at point F is plus 5.5. So for this positive sign, we will show the value which is in upward direction. So here is plus 5.5. Then bending moment at point E. So it is plus 7. So this is the point E. So we will show here the value plus 7. Then bending moment at point P. So this is the maximum bending moment. So I will extend this point P, and we will show the value plus 7.56. So this is the point 7.56. Then bending moment at point D. So it is equal to plus 6. So we have to show this below 7. So here is plus 6. Then bending moment at point C is plus 3.5. So this is the point C, and we have to show plus 3.5. And then next is bending moment at point A is 0. Now we have to connect all these points. So how to connect this? So if we observe from B to F, this is due to the this is due to the concentrated load or point load. So we have to connect these 2 points with constant linear line, because bending moment will vary linearly due to this point load. So I will show here from 0 to 5.5. Now next is E to F. So E to F also we have to connect with straight inclined line. Now next is D to E. So here is point D and here is point E. So how to connect this? So this is with uniformly distributed load, and uniformly distributed load, it will follow the parabolic law. So we have to show with curve. So I will connect all these points with curve. Then next is C to D. So here also with point load, so it will vary linearly, and then next with A to C. So it will also vary.